that in control system engineering part 2 we will be discussing the controller design part. Also we will be discussing, suppose you are given a controller and plan, that is plan transfer function and controller transfer functions are known to you. Now how will you post check the performance or analyze the performance and robustness? Okay, so what are the tools, means what are the indices we'll use for analyzing the performance and robustness of the feedback system? That we will be discussing first. Okay, and then we will start controller design, some simple controller design methods, mostly classical, to meet those performance and robustness norms. Okay. So first I will tell you what are the topics I will consider. As I have written here, the first topic that I will be considering is analysis of performance and robustness. So what are the performance we will consider, what are the robustness norms we will consider, that will come clearly. So first, under this major topic, the subtopics that I will consider is, what are the first we will see what are the control system design objectives, okay, and gain margin, phase margin. Phase margin, I think Professor Patro has already taught you, but I will go little bit into more details. I'll try to consider from practical point of view. What is gain margin? What is phase margin? And then gain margin, phase margin are as gain margin and phase margins are classical. You can say classical criteria for robustness. Then we'll see little bit of advanced criteria that are used mostly in aerospace industry. Those are sensitivity and complementary sensitivity margins. Okay. And we'll also try to see that when gain margin, phase margin criteria fails, gain margin, phase margin norms, and therefore sensitivity and complementary sensitivity norms are needed. Okay. So that's why sensitivity, complementary sensitivity functions will define, and what are their roles we'll discuss. And then we'll discuss that if we can meet sensitivity and complementary sensitivity some norms, then we can automatically meet some gain margin and phase margin criteria. But the reverse is not true. If we meet some gain margin, phase margin criteria, then we may not be able to meet sensitivity and complementary sensitivity norms criteria. But the reverse is true. That means sensitivity and complementary sensitivity norms are superior margins, better margins than gain margin and phase margin. Okay, that we will see. That is using this. So, what is the relation among sensitivity, gain margin, phase margin? We will discuss. And then the most important thing is that, suppose as I was saying, that you have to analyze the performance of the system. So how will you analyze? So we will be analyzing all the things using a loop transfer function. So you have been given a plant, you have been given a controller, you have been given the feedback interconnection. Then we'll study the behavior of the system using loop transfer function. So what is loop transfer function? That also I will come to. I will discuss. Professor Saurabh, I think, has already discussed this. Again, I will discuss. And how to predict the performance of the feedback system and robustness of the feedback system from the loop behavior, that we'll see. So that means, so to have some desired performance or robustness, the loop plot the board plot of loop transfer function should have some shape. So what should be the shape that we will consider? Okay. What should be the shape of board plot of the loop transfer function in order to achieve some desired performance and robustness? Okay. And then we'll consider also the what are the plots of corresponding plots of sensitivity and complementary sensitivity norms. S means complementary sensitivity, T means S means sensitivity transfer function, and T means complementary sensitivity transfer function. So it is not like that the loop behavior and the plots of ST are decoupled. So they are very much coupled there because sensitivity definition is coming from the loop transfer function. Because we will see that sensitivity equal to 1 by 1 plus Ls. Similarly, complementary sensitivity equal to 1 minus S. That will come. I do not know whether Professor Patra has taught these things or not, but anyway, I will be again discuss all the things little bit more details. Okay, and then we'll come to so these topics for to cover these topics. I will take approximately more or less 4 classes. Okay, so 4 classes I will take to cover this this topic: analysis of performance and robustness of a feedback system. So under this major topic, I will consider these subtopics as I discussed. Now, next I will go to the compensation methods. So, so I have already said that we will discuss under this topic. I will discuss the subtopic on a controller design objectives. So now we have to design the controller so as to meet those objectives. Of course, we will be in the undergraduate control course. We discuss classical controller. Those are used mostly in industries. Okay. Of course, nowadays modern sophisticated controllers are also being used in industry in order to improve the performance. But still, in industry, particularly in process control industry, not only process, even in aerospace control industries, also this classical controllers like lead lag lead controllers are used. Of course, if you see from one point of view, all controllers are lead lag or lag lead type. So the controllers that will be considering are of first order or second order type. Okay, lead lag all are first order controllers will be discussing, and lag lead controller will be second order because first order lag and first order lead. So remember that any controller are either lag or lead or lag lead, whatever it may be. I mean, so whatever higher order it may be. But for in your course, we will be discussing very simple controllers so that they can be easily implemented using op amps, using simple RC circuit, okay, or using op amp based integrated circuit. So the design method I'll be mostly discussing is frequency domain design method. So board plot will be used for designing this controller, lag lead and lag lead controllers. Of course, I'll be here, although I have not included. If time permits, then I will also consider root locus based design method for these controllers. At least I will give you my notes so that those who are interested they can go through it. Those topics. Root locus based design method. So frequency domain design method is very popular and very straightforward. And root locus based design method is little bit involved, but those who are interested, I'll share my notes with you for that part. And then on important topic that I'll be discussing is very much useful for designing controllers. That is pole placement based method. Okay. So pole placement based method we'll be discussing. Anyway, as you know that a system performance, a feedback system performance will be mostly depending on the closed loop pole locations. Okay, so closed loop pole locations now, what is the controller design objective? What is the objective of controller design here? So we will shift the poles at desired location. Arbitrary pole placement even we can achieve. We will see. We will be designing controller so as to achieve arbitrary closed loop pole placement. So this is a pole placement based design. So here this is a time domain method. Pole placement based method. A design is a time domain method. Ultimately, poles will be deciding based on pole locations. Will be deciding based on frequency, based on peak overshoot, settling time, all those criteria, and those poles will shift using a controller, feedback controller, and we will be using both 1 degree of freedom and 2 degree of freedom controller. I think you do not know what is 1 degree of freedom control and what is 2 degree of freedom control, but we'll slowly come into the those things. You will understand. Okay. So 2 degree of freedom control is very much important for uh, for for getting both frequent loop goals, better loop goals as well as response goals. So what are loop goals? What are response goals? That we'll see. Loop goals means your robustness, gain margin, phase margin, all those are called loop goals because those things will depend on your loop properties. And response goal means your closed loop input output system response, that is settling time, peak overshoot, steady state error, all those are response goals. So in case of 1 degree of freedom controller, so once loop goals are fixed, your response goals also becomes almost fixed. But using 2 degree of freedom control, we will see that we can somewhat the loop goals and response goal we can make independent. So that's why it is called 2 degree of freedom. Okay. So more details I will consider later, but just some some terminologies I have told here. The 1 degree of freedom and 2 degree of freedom. In case of 1 degree of freedom, the loop goals and response goals becomes dependent. Okay, loop performance you have fixed means into output response performance of feedback system also will get automatically fixed. But in case of 2 degree of freedom design, we will see 2 degree of freedom controller, the loop goal and response goal we can make somewhat independent. So that is the beauty of 2D of freedom control. Will come. And then of course more classical controllers, PI controller, PID controllers, those are used mostly in process industries, chemical plant, okay, process control plant. So those things also we consider. But I'll be giving much time on this controller design method or compensator. Controllers are also called compensator. Okay, control compensation or control design. So there are many terminologies: compensator, controller, filter. Sometimes also we call. Okay, filter mostly in signal processing respect we use filter, but sometimes we may also call filter. Okay, but mainly we say compensator or controller. So 7 to 8 classes I'll take. I'll give more emphasis on this discussing this topic. 7 to 8 classes I'll take on this topic, and then finally I'll be uh, I'll go to the sample data control system. Digital sample data and there is a difference between sample data and digital, although. So, so what is the difference? Why sample data digital control system is needed? So what is the difficulty, what are the limitations, how will you analyze the a sample data feedback system. So as you know, Laplace transformation you are using for analyzing a continuous time feedback system, right? Similarly, for sample data system, we will be using Z transform or Z transform for because sampled signal, discrete time signal, Z transform will be using for another. Their Laplace transform will not be applicable because Laplace transform is applicable for continuous time signal. For discrete time signal, we'll be using Z transform. Okay, so Z transform better. I will be discussing whatever is necessary, but better to brush up the Z transform little bit if you have studied those things in your mathematics course, transform calculus course. So there I will be discussing Z transform and how to study stability of a discrete time system and sampling theorem. I think some part of sampling theorem, Shannon sampling theorem, we have studied in your signal processing course. Aliasing effect also you have studied. So a little bit of touch I'll give you, and then controller design. So using a digital approach. So as you know, yeah, as you know that this you'll be this sample data control center is a vast thing. In fact, in our department, electronic department, a separate course is there, digital control system for postgraduate students. BTech students also can take as elective. So that's why all the things will not be able to take in these 4 classes. But whatever basic things are needed for designing a sample data feedback system that I'll discuss, and those basic topics will be very much helpful. We will see. So 4 classes I have kept for this mm, sample data feedback system. So total I need 4 plus 8 12 plus 4 16 classes. So I checked that I'll be getting 17 classes excluding your class tests. Okay, so 16 17 classes I'll get, so I think I'll be able to cover the topics, all these topics comfortably. Okay, so these are the topics, and I think Professor Saurabh Patra has already told the books, but for my part, again for your knowledge, yeah, information, I will say I used to follow these books because in one book you will not get all the topics good. In some books, some topics are good. In some books, some topics are not so well. Okay. So for example, if you want to have good graphs on modeling part, modeling of a feedback, modeling of a system is very important, right? This is the first step in designing controller. So physical, from the physics of the system, you have to model it. Okay, because we are interested in designing a model-based controller design, right? So model-based controller design, you have to have a model of the system. Of course, some modeling error will be there. Okay, so there's how to handle those modeling errors that we'll see. That is robust design, robust control system. That's why it is needed. But if you think about modeling, then Dot Bishop book, Modern Control Systems by Dot Bishop book is very good book. Okay. And then Modern Control Engineering by Ogata, it is a general book. Most of the topics are good. It is a you can take as the textbook. And then Automatic Control System is a very standard book. So this is also general. Means most of the topics are good. And this book I will follow. Automatic Control Systems by Ulovich, W.A. Ulovich. This book's price is maybe 300 or 350 rupees. You can buy. It's a very useful book. Okay, this is not that much thick, but it's a very good book. and many topics I will follow from this book. I will mostly follow automatic control system by Ulovich. So pole placement, 2 degree of freedom control. So 2 degree of freedom controller you will only get in Ulovich book. In Kuo and Ogata book, you will not get 2 degree of freedom control. And Ulovich, in Ulovich book, he started from the first chapter. From the first chapter onwards, he is general controller. So you may ask that why not 3 degree of freedom, 4 degree of freedom, how many degree of freedoms we can go? That will come. Okay, why 2 degree of freedom suddenly? Why not three or why not more? Okay, that we'll see. So these are the topics where in Ulovich book this is good pole placement design, 2 degree of freedom controller, and loop shaping. Loop shaping is also good. Loop shaping means you have to shape the loop transfer function using controller so as to achieve some loop goals. Okay, loop shaping, that is called. And then frequency domain design, as I was saying, lag lead controller design. I will not be following Ogata book and Kuo book, because in those books you will see those designs are not algebraic. They are trial and error based design in this Ogata and Kuo book. But in NK Sinha book, feedback control system, you will see that design is algebraic, very much algebraic. Some equations you have to solve, and then directly you can design the controller. Okay, so this is a very interesting book. This for frequency domain controller design. Okay, and then Norman Nice book is good for root locus based design. Also, modeling part is good. Nice book is also good book. Modeling part is good. Root locus, Nike's plot, all books are good. Raut Hari's stability, all books are good. In Norman Nice book, some interesting practical problems you'll get. Norman Nice and this book, Dot Bishop. Very good practical problems. Many practical problems to have considered in their exercise as well as in the examples. Okay. Well, so these are the books I will follow. And now we'll slowly start because we have very limited time. Let us start. Today I will not discuss many topics, but it's a very simple thing we'll discuss. Hopefully it will not be difficult for you. And if you face difficult, please ask me questions, because if you do not interact, then I will also not get interested. Okay, if you interact, then I will be very happy. Okay, so you must have doubt. If you do not have doubt, then I will understand you are not understanding. Okay, so this is control system design objectives. So as you know, this is the feedback diagram. So I have not shown what controller it is. It can be 2 degree of freedom, it can be 1 degree of freedom. So just one box I have written. So this is also plant, and this is sensor. So I have considered that actuator is there. Of course, actuator is embedded inside the plant. Okay. So for controller design, what do you do? Actuator and plant transfer function we multiply, and then we consider the whole as a plant. And sensor dynamics, remember that sensor dynamics we never consider. We normally do not consider for sensor dynamics part. Gain part we consider, but dynamics part we do not consider for controller design in general, because sensor dynamics is much faster than your plant and actuator dynamics. And sensor dynamics we consider as neglected dynamics, and your controller, as it is a faster dynamics, even if you neglect this sensor dynamics, your controller performance will not be bad, at least at low frequency. That we'll see. Why sensor dynamics we need not to consider. That will come slowly. You will understand. Okay, so this is the so all the controllers that I will be considering is output feedback based. State feedback based controllers we will not consider. No, state feedback based controllers are taught in control system theory course for MTech students. Of course, you can also take those as the subject as elective. So this is a disturbance. So disturbance is unavoidable in practice, as you know, and this is your measurement noise. So disturbance, what is the difference between disturbance and noise? Disturbance is a process disturbance, it is also called. So it is a low frequency signal compared to the bandwidth of the plant. Okay. And measurement noise is the is a high frequency signal compared to the bandwidth, the closed loop system bandwidth, but not bandwidth of the plant. I should say closed loop system bandwidth. Okay. Again, I am saying disturbance is a low frequency signal compared to the closed loop system bandwidth. Okay. Closed loop system bandwidth you can get if you have closed loop pole location. From there you can get time constant of the system, and from there, if you know the time constant of the system, what is the bandwidth? 2 pi by t will give you the bandwidth of the system. Okay. So disturbance signal, as I said, disturbance of the low frequency signal compared to the system bandwidth, closed loop system bandwidth, and measurement noise. Noise is the high frequency signal compared to the closed loop bandwidth. Okay. So this is the difference between disturbance and noise. So this is a feedback system. This is a control input. This is a reference input or comment. So this disturbance and it. So disturbance, reference, this noise, all are called exogenous signals. Okay. So this reference input we want to follow output. We want that output to follow reference input. But disturbance and noise will prevent the output to follow reference input, right? So disturbance and noise are unwanted signal, but reference signal we deliberately applying so that output will follow some trajectory. Okay, in missile also, in launch vehicle also, we try to follow some trajectory, right? So we generate some guidance path which the launch vehicle or such missile should follow. That is a reference comment. So DU is a controller output, or it is also called control input. So now what are the controller? Basic is a basic feedback control configuration. Now what are the controller design objectives? These are the very important for designing a controller. Uh, so first the primary objective is that you have to stability you have to guarantee. You have a feedback system. Now why feedback system is needed? Why feedback is needed? You may ask me that my system is stable system, say. Okay, for unstable system we need feedback, and for naturally system do not remain unstable, but we engineer it to make it unstable. For example, launch vehicle or missile, those are unstable. We engineer it. We need it to become unstable, right? So then we make it feedback to stabilize it. So if a system is stable, then the question arises that why, uh, if a system is stable, then why feedback is needed? So I think Professor Patro has already discussed this point. If a system is stable, then also we need feedback in order to uh, attenuate the effect of disturbance. Okay, so disturbance, for example, in case of a uh, speed control of a motor. Okay, Speed control of a motor, if you consider, suppose I want to run the machine, a DC motor say, I want to run the machine at 1000 RPM. Okay, so I have load. So if the load is smooth, there is not even without using feedback, I can run the machine at 5000 RPM even in presence of load. But if my load is not smooth, sometimes if the load is more, sometimes if the load is less, then what will happen if I do not use feedback? When the load is less, my speed will increase. When the load is more, my speed will reduce. Right? So in order to have a steady speed at steady state, constant speed, so we have to have a feedback also. So so for stable system, we need feedback in order to attenuate the effect of disturbance. This is a very important point. Okay. So for any system, feedback is needed for satisfactory operation. That's why once you use feedback, then you have to study. You have to guarantee it at least it nominal stability. So nominal stability is the minimum thing that we need. Nominal stability. And then robust stability, that is also needed. What do we mean by robust stability? That I will come. And then nominal performance and robust performance. So all this, so each topic I will discuss: nominal stability, robust stability, nominal performance, robust performance. All these topics I'll discuss in detail little bit. So all this we have to achieve subject to what? Some control effort constraint. Not only magnitude. Here I have written only the magnitude constant, but rate constant may also be there. Understood? Because this is a physical system, physical actuator. Actuator is a physical system, physical, so it cannot provide infinite controller output, right? Infinite control input. So if the control input magnitude is more, then what will happen? It will saturate. Okay, then nonlinear effect will come and sustained oscillation will arise and system feedback system will collapse. Okay, so all these control objectives has to be met subject to actuator constraints, actuator rate constraints, actuator magnitude constraints. All these things are there. Okay, so now, what is nominal stability? You know these things. That nominal stability means the closed loop system poles should be at least in the left half of S plane. This is for continuous time system. Similarly, for discrete time system, it should be in the Z, that we will discuss. It should be inside unit disks in Z plane. Okay. So this is a left half of S plane. Then robust stability means what? This is about nominal stability. Robust stability means what? Robust stability means, suppose you have assumed, when we are determining the closed loop poles, what we are assuming? We are assuming that the all are fixed. Plant is fixed, sensor is fixed, plant is fixed, sensor is fixed. Of course, controller nowadays we implement in digitally. We can assume controller fixed. There is no problem. There is no practical problem in it. So controller gains are fixed. That we can see. Nowadays there is those implementation of controller using those op amps and those filters. Those are gone. Nowadays all controllers we implement in digital processor. Okay, so controller gains we can assume to be fixed. So controller is fixed. So what is more practical then? Plant can vary. Plant parameters, whatever we have identified, whatever we have modeled. So suppose the plant poles we are assuming it to be s equal to -1, but it can be s equal to -1.5, or it can be s equal to minus zero point 0.5. So that may happen because of many physical temperature, change in temperature, change in humidity, change in the plant itself. some component may burn, many things may happen. Okay, so plant may change. So this is about, so whatever I was saying, that is parameter variation, plant parameter variation. Pole location is, instead of I have considered pole location, I have designed the controller considering the pole location to be at s equal to -1, but actual pole location may be s equal to minus 1.5. So this is about parameter variation. So another thing is that as I was saying, uh, so when we are designing controller, we neglect higher order dynamics. Okay, but the sensor dynamics is present actually. Sensor is not a static system, right? Most of the cases, rate gyro, position gyro, accelerometer, right? All are physical, all are dynamical system. Okay, so sensor dynamics, but but the sensor dynamics we are neglecting when designing the controller. But the controller should be designed such that even in presence of sensor dynamics, the system should behave as we want. So that means sensor dynamics acts as here uncertainty to the system. Okay. So that means sensor dynamics, what we are doing, we are deliberately neglecting. Sensor dynamics we are deliberately neglecting. That is called neglected dynamics. Okay. Or it may also happen that when we have modeled the plant, uh, some portion, some aerodynamics we have neglected. We could not model it. We tried to model, but we could not because we do not know the physics of that part. Okay, so that is called unmodeled dynamics. Got it? So one is neglected dynamics, another is unmodeled dynamics. So, but actually those things are present. So your controller has to be designed such that even if those things are present, my response should be, my system should at least remain stable. So that is robust stability. That means robust stability means what? The closed loop system should remain stable even in presence of uncertainty in the system parameters and neglected dynamics or unmodeled dynamics. As I told, I told many things. The neglected dynamics means deliberate neglected. As I said, sensor dynamics we are neglecting, and unmodeled dynamics means what? Unmodeled dynamics means some plant dynamics which we do not know the physics of the plant thing, uh, so that we are neglecting. Or sometimes even if we know that, we are deliberately neglecting so that my controller becomes simple, because if the plant order is high, controller order will be high. So that is a deliberately we are neglecting. Okay, so robust stability means that one, that means closed loop system should remain stable even in presence of uncertainty in the system parameters and neglected dynamics. And the nominal performance also, nominal performance means what? Your settling time, okay, peak overshoot, steady state error, all these things these are the time domain characteristics of a system. Okay, so your feedback system output should satisfy some settling time criteria, some peak overshoot criteria, steady state error criteria. Okay, those are nominal performance. Now robust performance, what? Even if you have neglected dynamics, even if you have parameter uncertainties, then even in presence of those things, your system performance should be close to the nominal performance. That is called robust performance. Right? That means system should ensure some desired performance close to the nominal performance, even in presence of those uncertainties in the system. That is called robust performance. Okay, and And I wanted to say here disturbance and noise. What is the difference? I already said these points that disturbance is a low frequency signal compared to the closed loop system bandwidth. Here I have not written although, but I will write in my final notes that when I will upload as compared to the closed loop system bandwidth. Okay, this is a closed loop system bandwidth. With respect to a system, I actually defined what is disturbance and noise. If a system is given, then noise disturbance means signals whose frequency lies much below its bandwidth, that is called disturbance, and the signals, unwanted signals, those whose frequencies lie much above, whose frequencies are much higher than the mm, bandwidth, system bandwidth, they are called noise. Okay. So as I said that disturbance and noise attenuation are very important thing uh, 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 because of so another point we should include that these are the criteria. Another is disturbance and noise attenuation. Okay, so disturbance attenuation is very important for stable system. So for stable system, feedback is only needed in order to have mm, your disturbance attenuation, because response characteristics you can easily shape using a pre-filter. Okay, but disturbance you cannot attenuate using pre-filter. You have to have a feedback, otherwise disturbance cannot get attenuated. So all these things we will discuss how feedback. I think Professor Patro has already gave you some idea how disturbance gets attenuated because of the feedback action. So I will also say when I will discuss disturbance and feedback, disturbance attenuation topic. Okay.
So,
Yeah.
so we are discussing nominal stability, robust stability, and all that when the value of u is less than u max.
Yeah.
So,
Yeah.
how are we determining the value of u max?
Emax is determined. It depends on actuator constant. The actuator is a physical system. My suppose my I have a motor, right? I have a motor. My motor my shaft can rotate up to this much plus minus theta max radian. That I know. Got it?
Okay, so
Or I
understood.
have a
So that's specified
yeah.
before, right? Like
Yeah,
that.
that is given to the designer. I have a motor which can I have a motor which acts as actuator, and actuator actuator maximum theta that the motor can rotate is the theta max that is given. For example, I should say pump. So whenever pump acts as actuator for for your rooftop tank, right? Rooftop tank water level control. Suppose you want to do, so their pump acts as actuator. So what is what is the pump voltage? Okay, pump voltage you cannot give beyond say 220 volt, right? Right, beyond
Yes.
220 volt you cannot give, so that is your actuator constant. You similarly, suppose in a missile system, I cannot give thrust beyond this much newton. Okay, got it?
Yes, understood.
Yeah, yeah. Okay, so we were discussing this point that robust stability I was discussing that yeah, robust stability. What do we mean by robust stability? Robust stability means capacity to tolerate uncertainties in the system. As I said, what are the uncertainties that we can have? One is parametric uncertainty. As I said, that because of some amplifier gain change, instead of pole at s equal to -1, it may become pole at s equal to minus 1.5 or s equal to minus 0.5. Dynamics or unmodeled dynamics, just one example here I have given. Suppose your plant is 10 by s plus 1 into s plus 10. So for controller design, what do we do? So because of dominant pole concept, this plan can be approximated as 1 over s plus 10 because this pole lies 10 times away from minus 1. So using dominant pole concept, I can approximate this one uh, by using 1 by s plus 1. Okay, so 1 by s plus 1. So but actually that's s plus 10. Suppose 10 by s plus 10 is your sensor. You can think about that. Your sensor dynamics is 10 by s plus 10 and your plant dynamics is 1 by s plus 1, and combinedly it is becoming 10 by s plus 1 into s plus 10, for which I have to design the controller. But for simplicity of controller design, I have I have I have I have made this simplification. 10 this transfer function I have reduced to s plus 10. So here neglected dynamics is 10 by s plus 10. So your controller should be designed such that I will be designing controller for 1 by s plus 1, but your actual controller has to be implemented for this one 10 by s plus 1 into s plus 10. So your controller should give desired performance for this one, but we are designing the controller for this one. That means here 10 by s plus 10 acts as neglected dynamic. Even in presence of this neglected dynamic, your controller has to be designed such that you get your desired behavior. Okay, so as you know, these are the robustness measures. As I was discussing, gain margin, phase margin, these are known as classical measures. And then infinity norms. What are infinity norms? Also, I'll be discussing. Just I have written this one here, but I'll discuss what is infinity norm. Infinity norm of sensitivity and complementary sensitivity transfer function. What is sensitivity? What is complementary sensitivity? That also I will come. So this is modern measure, and nowadays aerospace industries very much follow this sensitivity norm because they have understood that gain margin, phase margin will not suffice, and I will consider some practical example, flexible structure example where we'll see that gain margin, phase margin is good, but the sensitivity norm is very poor. Because of that, it is very much prone to uncertainties, very much prone to instability. Okay. So now I think just gain margin topic. Yeah, gain margin we'll consider. So I will define gain margin like this. So in many book gain margin they are defining in a different way, but I used to define and following Ulovich book or many other reference things, I will define gain margin this way. So don't, if you are asked what is gain margin, at that time don't say what is gain cost of frequency, what is board plot or so and so. Gain margin we should define, gain margin and phase margin we should define with respect to a feedback system, practical. It should have some practical meaning. So it should be defined like this, as I have said. So gain margin, what is gain margin? It is a factor. Okay, it's a factor by which the loop gain, EB terminology is very important here. Loop gain means gain of the loop transfer function. Okay, so again I am saying it is a factor by which the loop gain can be increased or decreased till the system remains stable. Okay. For example, if you have a system, suppose I have a plant is GS, controller is CS, it is a negative feedback system. So initially loop gain is what? Suppose I have added, so loop gain means this is a feedback loop gain. So initially K equal to nominal, what is the nominal loop gain? Here there was no gain. No gain means nominal gain was 1. K is equal to 1 under nominal condition. So how will you obtain gain margin? Here you will just increase k equal to 1 is the nominal value. You will increase k equal to from k equal to 1 to higher value till the system remains stable, right? Or or one thing, it may be also the case that k you may decrease from 1 to the lower value till the system remains stable. That means the fact k equal to 2, it becomes unstable, and say, and also k equal to zero point 0.3, say it becomes unstable. So what is the factor you have increased? Factor you have increased is 2, right? And what is the factor you have reduced? What is the factor you have reduced? 0.3 is the factor you have reduced. So I will say these things as two terminology. One is upper side gain margin, another is lower side gain margin. So the factor by which the loop gain can be increased till the system remains stable is called upper side gain margin. Got it? Again, I am saying the factor by which the loop gain can be increased till the system remains stable, it is called upper side gain margin. And what is lower side? The factor by which the loop gain can be decreased or reduced till the system remains stable, that is called lower side gain margin. Got my point? Suppose k equal to 1 is the nominal value, nominal gain. So and the fact and the system remains stable from k min to k max. What is the increased side or upper side gain margin? Increased side or upper side gain margin is k max. What is the lower side or decreased side? I have written increased side or decreased side. It is also called as upper side and lower side. What is the lower side gain GM? Lower side GM is your k min. Okay. So well, today I will stop here, and in the next class we will continue. Okay, tomorrow I will take class. So in this week I will take live class, and let us see how it goes. Depending on your feedback, I have also videos ready with me for me. I can upload, no problem. But I like to take live classes. Now it is up to you what you will follow. But at least this week I want to take live classes. Okay.